Ladies and gentlemen, hello and coming to you not quite live from One Take Studios, where we are going to have some fun today. Alright, we are going to analyze the heck out of some graphs here, okay? And so for starters, we're just going to do some observations, and to do that, I would like to switch to my calculator screen. Alright, so check this out. I've prepared some graphs for you that are just parent functions, alright? Nothing fancy, this is just the graph of y equals x, or f of x equals x. Basic line, no frills, no changes. Notice it's x to the first power, and take an observation for a moment. Where are the ends of this graph going? All right, so just think about that. We're going to go to the next page here. This is x squared. X squared. That's a degree of 2. That's an even number. What are the ends doing this time? Interesting. What about the third screen? Ooh, x cubed. That's a 3. 3s are odd numbers. What are the ends doing? X to the first power, odd number. What are the ends doing? X to the third power, odd number. What are the ends doing? X to the second power, even number. What are the ends doing? All right, I'm going to come back to that pondering in a moment after I show you something, because seriously, I just have to show you something. These graphs all have names. So the linear one is a line. The parabola one is a parabola, quadratic. This is a cubic function. It does not have a name, and it seriously should have a name. So some of you guys know that I call these graphs Travoltas. And you don't really understand or believe me as to why, so I want to show you this, okay? Here is why cubic graphs are Travoltas. Look at that! Look at that man! Look at his dance line! Boom! That is a perfect cubic equation right there. That is negative 0.2x cubed. I graphed it and put it on there. So when I refer to this as being a Travolta, this is why. Dude, check it out. 70s disco right there. Okay? Alright, back to our observations again. Next screen. This is x to the fourth power. X to the fourth power, that's an even number. What are the ends doing? Are you formulating any opinions just yet? One more, here's x to the fifth. X to the fifth, 5 is an odd number. What are the ends doing? Have you come up with anything? Maybe, possibly, kind of, sort of. All right. So let's see what you think, and let's do some recording of our observations here. If we have an odd degree, so it's x to the first power, or third power, or fifth power, or 28th power. Oops, I lied. 29th power. There we go. These are all odd degrees, and so if we look and if we observe the ends of the graphs, the ends go opposite directions. One of the ends goes up, one of the ends goes down, but the ends are going opposite directions. Okay, and what was happening for our even powers? Well, think about a parabola, because that's probably the most common one that comes to mind there. With even degrees, both ends of the graph go the same direction. So ends go same direction. And this will be true then for all even powered polynomials or all odd powered polynomials. By the way, John Travolta may be sometimes construed as odd, and therefore it goes opposite directions, if that helps or not. Up to you. All right, let's see. So what else? Let's go back to our screen again, take another peek. Got a couple more slides there prepared for you. I gotta go to this screen. There we go. Okay, so next slide up. That's a little complex looking. All right, two equations graphed on the same screen. This one is x to the fourth. This one is x to the fourth. So this one is, what is that? Red, brown, something like that. But both ends are going up. Why? It's a fourth power, so both ends go up. This is, again, a fourth power. What are the ends doing there? Both going down. So now what do you think is the difference between these? Why, if both ends are going the same direction, for this equation, why are they going up, versus for this equation, why are they going down? Did you catch it? Did you see it? It makes sense. Look at my first term here. This is a positive x to the fourth. This is a negative x to the fourth. Ladies and gentlemen, if it's even, the ends go the same direction. Positive goes up and negative goes down. All right, so that should make some sense. And then one more of a similar nature going right here. Oh, again, relatively pretty. This one is x cubed. This one is also x cubed. All right, so let's follow the red line here for a moment. How do we read? We read going from left to right, correct? Left to right. So follow the red line from left to right. We're starting down and we end up going up. We started down and we go up, 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 up. This is a positive x cubed. Follow the other line. Follow the black line. Left to right going down. This one is negative, all right? So, with our odd degreed functions, as we read left to right across the screen, if ultimately the graph is going up, it's because it has a positive leading coefficient, and if ultimately the graph is going down, it's because it has a negative leading coefficient. All right, so all of this should be relatively logical. Let's go back to our recording of our notes here for a moment. So, positive, what happens for odd as we go from left to right, the graph goes up. And if it is a negative leading coefficient, as we read from left to right, the graph goes down. Okay, and then for the even stuff, if we are talking positive, then both ends go up. Both up. And if we are talking negative, then we are saying that both ends are going down. All right, so just some basic observation stuff there. Every time you go to graph, which ultimately we are going to graph something today, you should have an idea in mind of the general shape, what the ends should be doing, which direction it should be going. All right, now, I have some bad news. And I only say it that way because you're about to be really afraid of what I wrote on the bottom of this paper, okay? So take a deep breath. Promise me you're not going to panic, okay? No panicking. Here we go. All right. Normally, when we talk about the ends of the graph, and we talk about the behavior, we say, well, they're going up, they're going down. Okay, great. This is the more formal way to describe that. If a textbook is talking about the end behavior of a graph, they're referring to two statements that are very similar to these. Sometimes you'll see slight rearrangements, but it's the same thing. This is not nearly as scary as it looks, but until we decipher it, it's going to look kind of crazy. Okay? So let's start here. This is an x, and this says goes. So x goes to negative infinity. Picture the x-axis. X-axis. Which way along the x-axis goes to negative infinity? Negative infinity, that would be to the left. So ladies and gentlemen, all this is saying is we are describing what is happening on the left side of the graph. This is the left side. This one says, all right, as the x's go to positive infinity. Again, x-axis, which direction is positive infinity? Heading off to the right. So this statement describes the right side of the graph. You will always have two statements because your graphs have a left side and a right side. And this is saying what's happening on the left side, and this is saying what's happening on the right side. I will always have one positive infinity and one negative infinity, because if I had both positive, that means I'm going to the right twice. That doesn't really make sense. And if they're both negative, then they were going to the left twice, and that doesn't really make sense. So always one positive, one negative. There we go. So what is the first part of this? F of x. That's the same thing as y, isn't it? So this is saying my y's are going somewhere on the left. So let's think this through. The y's are going somewhere on the left. Where might the y's go? The y's axis goes up and down, so this is going to have to be something that says either up or down. And again, down here, this is going to be f of x, same thing as y. Where are the y's going? Well, on the right, again, the y's, the y-axis goes up and down. This is going to be describing, is the right end going up or down? Is the left end going up or down? And ultimately, it comes down to fill in the blank. I need a symbol for each of these. And again, I need two phrases because each graph has two ends. What's this going to look like? All right. I got two examples I want to walk you through just for comparison's sake here. All right, so let's go with this lovely thing right here. Okay. I have no idea what the equation of that graph is. I just made it. And quite frankly, I don't need to know. I just need to observe what is happening with this. Okay. So if I take a peek at this, I would say, in behavior, I would say both ends are going up. Okay, great. How do we write that in our formal language? How do we write that both ends are going up? First statement. Well, again, so what is this one saying? X is going to negative infinity. x-axis goes left to right, negative, that's to the left. So this is asking what's happening on the left. This is the left side of my graph. What's happening? It's going up. The y's are going up. How do you think I write up? How far up does it go? Forever. So how do I write that it goes up forever? Positive infinity. So the y's are going to positive infinity. The y's are going up as the x's are going to negative infinity as the x's go to the left. So towards the left, we are going up. If you don't like infinity, turn it sideways and make an 8. That's great. I've got some people that look at this as being like a potato chip. So this is like negative potato chip. If that makes you happy, great. All right, but again, we have to have 2 of these phrases because there are 2 ends of the graph. So again, we are looking at fill in the blank. This is saying as the x's go to positive infinity. Here's my x-axis. Positive infinity is this way. This is saying, hey, what's going on the right side of the graph? On the right side of the graph, this one is going up again. So the y's are going up. How do I write that? Going up forever and ever and ever. Positive infinity. Okay? This would be the official way to write the end behavior for a graph that looked like that. And again, based on what I saw over here, if I didn't even have the graph, I could look at it and say, hey, I've got an equation that is an even degree and it's positive. I know what the ends are going to do. Yay me. All right, one more of this variety. Another graph. I made it up. I have no idea what this equation is, and it doesn't really matter right now. But again, it is a graph, and I'm looking at what the ends are doing. I would say the left is going up and the right is going down. How do I say that formally? All right, how do I say that formally? So again, this is x is going to negative infinity. X-axis, negative is this way. So this is saying what's happening on the left. On the left, what's the graph doing? It's going up. How do I say it's going up? Up. Just like before. Okay. But this time, when we go to the right is not going up. All right, so this is as x goes to positive infinity. Here's my x-axis, positive infinity. What are the y's doing? Where are the y's going? They're going down. How do I say down? Well, again, how far are they going down? They're going down for forever. So negative infinity. And that would be another example then. All right, so end behaviors, if a textbook is talking, this is the kind of language that they are speaking right here, and there's a couple of examples for those. Okie dokie. All right, one last thing for you today, so one last piece of this topic, and that is going to be not dealing specifically with end behaviors, but in general, dealing with graphs. All right, so let's think about what could happen here if I would like to graph something. I've got this knowledge of what the ends are doing. So if I look at this right now, I already have a thought in my head. My thought is, this is cubic. John Travolta, it's a Travolta graph. And that means it's odd. So I've got one end that'll go up and one end that'll go down. So I know to expect that already. And this is a positive leading coefficient. This is a positive x cubed. So as I read left to right, ultimately this graph should be going upward. And so now I know what to expect. So I got this big old graph grid with nothing on it yet. How do I get this from my calculator accurately onto paper? Because I do want to use my calculator to help me out. It's nice to be able to use our technology, but we have to know how to use it. So I'm going to jump back to this other screen again. There we go. And go into our next page, which looks like this. Looks like this. Ah, yes. All right, so that's the equation that I had written on my paper, x cubed plus 4x squared plus x minus 6. Here's what it looks like, and I'm looking for a good way, an accurate way, to transfer this onto paper so that I can actually show off my graphing skills for this. What might I do? Well, one of the first things I might do is pull up the table. Control T for table, Control T. And this is the 11th function that I've got programmed right now, so I put this on the 11th function. So these are my x's and these are my y's. Why do I have this brought up here? Because this is so helpful. I want to know where this thing is going. Ooh, and I can see, check this out though. All right, so negative 8, as we go to the left, as the x's become negative, this thing is definitely going to negative infinity because negative 270 is halfway there, I think. All right, so points that I might actually graph. Well, negative 410, I may or may not graph that one, but I would like to know where that end is headed. So I'm going to jot that one down. So I'm making a list on my paper right now of points that I would like to consider for my graph. So negative 410 is one of those. Obviously, these next two are going to be good. So at -3, 0 and -2, 0, those are going to be our x-intercepts, so those are probably important. -1, -4 also seems like that's pretty much graphable, so I like that one. 0, -6, that's my y-intercept, so taking notice of that one. 1, 0, ooh, there's another x-intercept. I want to use that one. Ooh, 220. Ooh, 220. I might not want to graph that one, but again, I'd like to know where the graph is headed, and now I can see on the right with my positive x's, that thing is headed to positive infinity, because those values are rising quickly. All right, so I've jotted some of those points down so I know to use them. And then I'm going to jump back and get rid of this table again. So again, Control-T brought the table up. Control-T will take the table away. What other points do you think might be useful in this graph? There are these things here that are called turning points. If this was just a parabola, we would call that the vertex. That's called a turning point. This graph has 2 turning points, and I would like to know where it turns, because those are important points in the graph. So to find where it turns, well, everything fun and exciting is in the menu. I'd like to be able to analyze this graph. Does this graph have a maximum? Not really. I'm going to click maximum anyways, but it goes up for forever. So does it really have a maximum? No, but this piece of the graph right here has its own maximum. It's called a local maximum, and I can ask the calculator to help me find the local maximum by telling it which piece of the graph to look at. So my little tiny vertex there, I've got my line to the left is the lower bound. So click enter on that, slide it over, and the piece of the graph that I select, hitting enter again, is the piece of the graph that will analyze for me. So that turning point is -2.54, 0.879. I'm going to make a note of that. -2.54 and 0.879. There we go, there we go. All right. I would also like to know the other turning point, which again is not going to be the lowest point of the graph because this graph does go to negative infinity, but I want to analyze that section of the graph. So again, going back to my menu, analyzing the graph, this time I would like to know the local minimum. So I'm selecting minimum, and I'm going to set just to this piece of the graph. So from here to here, I would like the calculator to analyze that section. And there is my local minimum. So making note of that, -0.131, and then -6.06. All right, now I'm in a really good spot. So now if I go back to my other screen and say, okay, I'd like to graph this, I've got a whole bunch of information and everything that I might possibly want to use to graph this thing and make it look good. Points that I like: -3, 0, -3, 0, -2, 0, -1, -4, 1, 2, 3, 4. There we go. 0, -6. That's 4, 5, 6. 1, 0 is back up here again. All right, so at 2, I'm at 20. I'm not going to graph that one, but I know this is going to be a really sharp rise. And even for -10, while I probably could graph that one, I probably won't. I know it's going to be a pretty sharp fall. Again, we said it's odd, and we said that it's positive, so we know it's doing something left to right, rising ultimately. -2.54, so -1, -2, so roughly -2.5. We're coming up not quite 1 at 0.879, so that's going to be my local maximum, so one of my turning points. And then, ooh, that is just below 0, and just below -6. So kind of right next to that y-intercept is where my other turning point is located. This is kind of a sharp dive. I'm going to stick close to the points I know. Turn at the turning point. Aim for the next point. Aim for the next turning point. Sharp curve coming back up through this thing. And again, I know it's a really sharp rise, so I'm going to stick to the points I know. And know that this is headed for 20 and this is headed for -10, but it's not there yet. There's my graph. All right, so this is just about paying attention to detail. You can do this. The other stuff with the end behaviors, that just takes a little bit of practice. I promise you that you do get used to it. And just know the general what's supposed to happen with the graph, because you can prevent yourself from making a whole ton of mistakes of all kinds of type of things if you understand what the graph is supposed to be doing. Okay? All right, have fun and enjoy and put this to practice.